The European Particle Centre for Research, CERN, is releasing information today about a brand new particle accelerator, twice as deep and 3 times larger, which has uncovered 3 new particles that could assist us in understanding how the universe was born and how it will develop in the future. Just recently, researchers at CERN revealed findings that turn our perception of the universe upside down. Beneath the surface of their revolutionary experiments lie particles and strange forces that seem straight out of a sci-fi novel. From openings that could lead to other dimensions to particles that pose a threat to the very foundations of reality, these experiments are filled with secrets. Let us enter the world of CERN and discover information that may redefine our universe. Some believe it could be the entry point to new dimensions, where a wormhole might conceivably appear in the sky without warning, all due to the groundbreaking research carried out at the Large Hadron Collider, LHC, located at CERN. The LHC is the world's largest and most effective particle accelerator, situated on both sides of the border between France and Switzerland. This bizarre phenomenon is shrouded in mystery. Some claim that an organization not known to the public has knowledge of secrets that may change our understanding of physics. The European Organization for Nuclear Research operates this massive scientific instrument. It stretches for 27 kilometers, deep beneath the surface. The primary purpose of the LHC is to allow physicists to test claims made about a variety of particle physics theories. This includes the well-known examination of the Standard Model of particle physics, which helps us comprehend the fundamental building blocks of the universe. The LHC functions by accelerating protons to nearly the speed of light before colliding them with one another. These collisions result in a flurry of fresh particles that researchers study to gain insights into the laws of nature. It was through such experiments that the Higgs boson, often referred to as the God particle, was discovered in 2012. This discovery confirmed how particles gain mass and marked a turning point in particle physics. Experiments at the LHC are essential for comprehending phenomena that occur under extreme conditions, similar to those immediately following the Big Bang. The data collected helps us learn more about the beginning of the universe, its evolution, and the fundamental components of matter. The LHC also plays a role in revealing new facets of reality, possibly even new dimensions, that may shed light on dark matter and fundamental forces of nature. However, CERN's advanced experimentation is not without concern. Some speculate that high-energy experiments could create strange objects or black holes. Despite these fears, CERN ensures that all safety precautions have been taken, and the scientific community keeps a close watch. Theoretical models demonstrate that such risky scenarios are extremely unlikely. Through ongoing research, CERN's discoveries improve our understanding of the universe and showcase the amazing capacity of human ingenuity and collaboration. The Large Hadron Collider is a modern marvel, more than just an impressive piece of technology. It is situated beneath the French-Swiss border and traverses a tunnel 27 kilometers in circumference and up to 175 meters in depth, making it the largest underground particle collider in the world. The LHC structure is designed to conduct experiments on an unprecedented scale. A tunnel housing the collider, with a diameter of 3.8 to 8 meters, contains 2 adjacent parallel beam pipes that cause protons to move in opposite directions. These are accelerated by a series of superconducting magnets, which are essential for maintaining the protons' paths and adjusting their trajectories at speeds near the speed of light. The beam pipes are surrounded by advanced cooling systems that maintain a temperature colder than outer space, necessary for keeping the superconducting magnets functioning properly. The scale of the LHC is further highlighted by the thousands of magnets it uses, including 1,232 dipole magnets for bending the beams and 392 quadrupole magnets for focusing them. The largest superconducting magnets are 15 meters long and weigh 35 tons each. At the heart of the LHC is a mission to investigate the universe's fundamentals by observing the tiniest particles. By accelerating particles to near light speed and colliding them, the LHC allows physicists to study the resulting subatomic fragments. This helps test and refine our understanding of the Standard Model, currently the most accurate description of the subatomic world. One of the LHC's main goals is to explore the mysteries of the Higgs boson. Its 2012 discovery at CERN confirmed theories about how particles acquire mass. The LHC also explores other fundamental particles and phenomena, addressing critical questions such as the nature of dark matter and the universe's earliest moments after the Big Bang. The collider seeks to detect new particles predicted by theoretical physics but not yet observed. These experiments could reveal new physics beyond the Standard Model, including hidden dimensions and supersymmetry. The LHC embodies a larger-than-life vision, not only to understand the universe's building blocks but also to foster global collaboration. Scientists from more than 100 countries work together at CERN, making the LHC a symbol of international cooperation in the quest for knowledge. Thanks to its size and design, the LHC is equipped to tackle some of the most profound questions in physics. Its purpose extends beyond pure science. It also aims to inspire global cooperation and push humanity's understanding of the universe. At the core of CERN's research, the LHC is a powerful tool for examining the quantum space. It allows scientists to observe and analyze the fundamental elements of the universe. Particles are accelerated and collided inside ultra-high-speed vacuum tubes, guided by superconducting electromagnets cooled to temperatures even lower than space. These collisions generate a range of subatomic particles, many of which are highly unstable and exist only for fractions of a second. To observe and study these events, the LHC is equipped with massive detectors like ATLAS, CMS, ALICE, and LHCb, each tailored for specific types of research. These detectors collect data about mass, charge, and momentum, helping physicists validate theoretical predictions and understand the forces that govern the universe. One of the LHC's most notable results was the discovery of the Higgs boson in 2012. This particle is critical because it provides evidence for the Higgs field, responsible for giving elementary particles their mass, a major milestone that confirmed long-held predictions. In addition to the Higgs boson, the LHC has enabled the discovery of other exotic particles, such as pentaquarks and tetraquarks, composed of 5 and 4 quarks respectively. These discoveries have expanded our understanding of hadronic matter, matter composed of quarks bound together by the strong force that holds atomic nuclei together. Despite these scientific triumphs, some speculative concerns remain. Among the most discussed theoretical threats are the potential creation of strangelets or miniature black holes. Strangelets are a hypothetical form of matter more stable than ordinary matter. The fear is that if strangelets were created, they could trigger a catastrophic chain reaction by converting everything. These theoretical threats, while captivating, have been largely addressed through rigorous scientific investigation. CERN's comprehensive safety protocols and the oversight of the global scientific community have provided reassurance that the experiments conducted at the Large Hadron Collider pose no existential risk. Instead, they continue to yield groundbreaking insights into the very nature of matter, energy, and the origins of the universe. One of the LHC's most exciting pursuits is the study of dark matter, the invisible substance that makes up roughly 27% of the universe. Although it cannot be directly observed, its gravitational effects on visible matter suggest that it plays a crucial role in the structure and evolution of the cosmos. By examining high-energy collisions, scientists hope to detect particles that may serve as evidence of dark matter's existence, such as neutralinos or other supersymmetric particles. Moreover, the LHC is also instrumental in exploring the possibility of extra dimensions beyond the familiar three spatial dimensions and time. Some theories, like string theory, suggest that additional compact dimensions exist and could potentially be revealed through subtle deviations in the behavior of particles. If such dimensions were to be detected, it would revolutionize our understanding of space, time, and the fundamental architecture of the universe. Another major area of focus is the imbalance between matter and antimatter. According to the Big Bang theory, matter and antimatter should have been created in equal quantities, yet our universe is dominated by matter. This mystery, known as baryon asymmetry, is something the LHC is uniquely equipped to investigate. Through the study of rare particle decays and interactions, researchers aim to uncover why our universe favors matter and what happened to the missing antimatter. As experiments at the LHC become increasingly sophisticated, new upgrades are continuously implemented to enhance its capabilities. The High Luminosity LHC, HLLHC, project, currently underway, aims to increase the collider's luminosity by a factor of 10. This means more collisions, more data, and an even greater potential for discovering rare phenomena. When completed, the HLLHC will allow physicists to study particles with unparalleled precision and possibly uncover new physics that has eluded detection so far. The LHC's data processing infrastructure is also a marvel in its own right. Each second, the detectors produce enormous volumes of data, far more than can be stored. Sophisticated algorithms and artificial intelligence systems are used to filter, sort, and analyze this information in real time. Only the most interesting events are saved for further study, representing a triumph of computational science working in tandem with experimental physics. Beyond its scientific and technological achievements, CERN also serves as a model for international cooperation and peace. In a world often divided by politics and conflict, CERN brings together thousands of scientists, engineers, and students from over 100 countries to work toward a common goal, expanding humanity's knowledge of the universe. This collaboration fosters not only scientific advancement but also cultural exchange and mutual understanding. The impact of the Large Hadron Collider extends far beyond the scientific community. Its discoveries have inspired generations, influenced educational curricula, and fueled imaginations around the globe. It reminds us of the importance of curiosity, the value of persistent inquiry, and the incredible things we can achieve when we work together toward a shared vision. As the LHC continues to delve deeper into the mysteries of the universe, one thing is certain: the quest for understanding is far from over. With each collision, each data point, and each breakthrough, we inch closer to answering some of the most profound questions ever asked. What is the universe made of? How did it begin? And what lies ahead in the grand cosmic story? The answers may still be hidden in the subatomic shadows, but thanks to the work at CERN and the Large Hadron Collider, we are better equipped than ever to find them. Hadron Collider, they probably would be extremely unstable, and they degrade too quickly to cause any changes to the Earth's matter. In addition, cosmic rays, space-based high-energy particles, frequently strike the Earth with energies significantly higher than those produced by the Large Hadron Collider, LHC, without generating any harmful effects. This unorthodox natural experiment demonstrates that strangelets are not a legitimate threat. The notion that the Large Hadron Collider could produce micro-black holes stems from theories of extra dimensions in physics, as described by some theoretical models. The LHC's energy collisions might generate small black holes, but these would evaporate quickly as a result of a process known as Hawking radiation. Experts, in the wake of physicist Stephen Hawking, concur that if tiny black holes were ever made at the LHC, they'd pose no real threat. Such black holes would be incredibly insignificant and would evaporate before they could interact with the environment. Second, the LHC's energy requirements for collisions, despite their scale, are significantly lower than the collisions of cosmic rays that occur naturally between human standards. Since no harmful micro-black holes have been observed from cosmic ray interactions, it's unlikely that any would be produced by the LHC. Rigorous safety checks are also carried out by independent committees to ensure that there is no danger posed by LHC-based experiments. Theoretical investigations, experimental data, and safety guidelines are included in these reviews to deal with any potential dangers. While the LHC's experiments keep pushing the boundaries of our knowledge of physics, they are conducted with high scientific quality and responsibility. Oversight guarantees that humankind can benefit from cutting-edge discoveries without taking unnecessary risks. Theoretical risks frequently sound more like science fiction than actual science. The scientific consensus, based on comprehensive research and natural cosmic events, is that the Large Hadron Collider is safe. The oddest of risks are minimal. One of the most intriguing proposed unconventional experiments involves the investigation of magnetic monopoles. A monopole is a hypothetical magnet-like particle with a single magnetic pole, such as only a south pole or only a north pole. Typical magnets always possess both a north and a south pole. Predictions of magnetic monopoles were made by physicist Paul Dirac in 1931, who demonstrated that their existence would explain the quantization of electric charge, implying that charge is only available in discrete amounts. Despite their theoretical significance, magnetic monopoles have never been found. Researchers at the Large Hadron Collider have been looking for proof of these mysterious particles. If discovered, magnetic monopoles could radically alter our perception of magnetic fields and offer the potential for significant technological advancements, including the creation of new types of energy transmission and storage. Likewise, the discovery of magnetic monopoles would make it possible to test evidence for overarching theories like string theory, which tries to unify all fundamental natural forces within a single framework. The search for magnetic monopoles may seem mysterious, but it exemplifies the adventurous spirit and scientific curiosity that drives inquiry at CERN. The search for such rare and potentially revolutionary particles demonstrates the Institute's dedication to exploring the unknown and broadening the frontiers of human knowledge. Another extraordinary experiment at the Large Hadron Collider involves exploring the possible existence of particles that could travel faster than light. According to Einstein's theory of relativity, the speed of light is the universal speed limit. However, some theoretical models suggest that tachyon-like particles could exist, which would always move faster than light. The detection of tachyons would fundamentally challenge our understanding of spacetime. While most physicists are doubtful of their existence, the search for such particles at the LHC signals the facility's willingness to investigate even the most speculative aspects of theoretical physics. Additionally, the Hadron Collider allows scientists to carry out experiments that replicate conditions in the early universe, specifically, the immediate aftermath of the Big Bang. High-energy collisions produce a state of matter called quark-gluon plasma, which existed only for a few milliseconds after the Big Bang. By investigating this plasma, physicists hope to gain a deeper understanding of how the universe transitioned from a high-energy state to the complex and structured cosmos we see today. Fundamentally, these novel experiments at CERN, including the search for magnetic monopoles and the creation of quark-gluon plasma, emphasize the scale and purpose of scientific investigation carried out at the LHC. They demonstrate CERN's commitment to pushing the limits of our understanding and exploring new areas of physics that were once considered purely theoretical. The ultimate goal of the Large Hadron Collider is to push human understanding of the cosmos to its limits. By colliding particles at unprecedented energies, it allows researchers to investigate the fundamental properties of matter and the forces that govern the universe. This ferocious endeavor to comprehend the unknown demonstrates humanity's deep curiosity and desire to explore. The findings at the Large Hadron Collider have had profound repercussions for our comprehension of the universe. Through inquiry into matter's smallest building blocks and the fundamental forces at play, these experiments help us learn about the universe's origin, evolution, and fate. They provide insights into the very foundation of reality and help address some of the most important questions regarding existence. The technological progress and scientific advances resulting from LHC studies also have practical applications beyond particle physics. These include the development of advanced data systems, computing technologies, detector innovations, and analytical techniques. Such advancements contribute to progress in fields like materials science, medicine, and information technology. Experiments at the LHC also encourage international cooperation and inspire new generations of scientists. Researchers from around the world collaborate, sharing knowledge and expertise. This global cooperation is key to unlocking the mysteries of the universe and highlights science's ability to transcend borders and unite humanity. In conclusion, the Large Hadron Collider is a cornerstone of modern physics, enabling groundbreaking discoveries and advancements in our understanding of the universe. Its experiments reveal the nature of fundamental forces, particles, and the origins of matter, offering invaluable insights into the mysteries of existence. Through technological innovation and international collaboration, the LHC stands as a testament to the spirit of scientific research and humanity's boundless curiosity. As we continue to explore the universe, we do so with the LHC guiding us toward answers to the most fundamental questions about our world and our place within it. Beyond its contributions to fundamental physics, the Large Hadron Collider, LHC, also plays a pivotal role in fostering global partnerships in science. With thousands of physicists, engineers, and technicians from over 100 countries, the LHC stands as one of the most collaborative scientific endeavors in human history. This worldwide network not only advances research but also strengthens diplomatic and cultural ties, showing how science can serve as a unifying force even in a fragmented world. Moreover, the LHC's infrastructure and data handling requirements have driven unprecedented advancements in computing. The development of the worldwide LHC computing grid, an enormous distributed computing infrastructure, has enabled researchers to process and analyze vast amounts of data efficiently. This grid has inspired innovations in cloud computing, big data analytics, and cybersecurity, with ripple effects across industries and academic fields far beyond particle physics. The educational impact of the LHC cannot be overstated. It serves as a dynamic training ground for young scientists, engineers, and researchers. Students working on LHC projects are exposed to cutting-edge technology, collaborative research environments, and some of the most profound scientific questions of our time. Many of these young minds go on to apply their expertise in diverse sectors such as aerospace, medicine, finance, and environmental science, enriching society through the cross-pollination of skills and ideas. Public engagement is also a key priority for CERN and the LHC. Through exhibitions, open days, virtual tours, and educational outreach, the LHC continues to captivate and inspire the public. By demystifying complex scientific concepts and involving citizens in the wonder of discovery, the LHC promotes scientific literacy and encourages the next generation to pursue careers in science and technology. As the LHC moves into future phases, such as the high-luminosity LHC upgrade, its potential for discovery only grows. The upgraded collider will allow for even more precise measurements and the possibility of uncovering new particles or interactions that could reshape our understanding of the universe. Scientists hope to probe deeper into questions surrounding dark matter, antimatter, and the unification of forces, areas where existing theories remain incomplete. In this ever-evolving journey, the LHC embodies humanity's pursuit of knowledge. It represents the courage to ask difficult questions, the patience to explore complex answers, and the ambition to push the limits of what is known. Through meticulous research, innovation, and global collaboration, the Large Hadron Collider continues to illuminate the fundamental truths of our universe, truths that may one day transform not only our understanding of the cosmos, but our place within it.